press the go button. One each. All right. How are you guys doing? Are you all right? How are your brains? Are they still taking in information, or have you gotten to the point where things are starting to pass you by? I would completely understand if things are starting to pass you by. I confess I tried to concentrate this morning. It didn't go so well. I found it a little bit difficult. How are you guys finding the concentration levels? Are you coping okay? Are you resting? Or are all your family making the same demands of you as they always do, even when you don't have study? I'm seeing some smiles. Tomorrow is Friday. Well said, Adriana. Yes, yes. Unfortunately, when Friday is a tough day, it makes getting through Friday to get to the weekend just that little bit harder, doesn't it? I'm going to try really hard to go easy on you today. I'm going to talk slower and more softly, mostly because my energy levels are probably just as low as yours are. Sandra and I are like, oh, we're struggling just a little bit, so completely understand if you guys are as well.
Well, we'd like to maybe shake up the dynamics a little bit.
Yeah, we'll shift it around.
Group work.
Yeah.
And, you know, today we're pretty much doing what we did last week with the platform building, and we're looking at the structural systems and the service systems that go into those buildings, but we'll be doing that for our apartment building and for our warehouse. So once we deliver a little bit this morning about different construction types that you could use on those types of buildings, then we're going to sit down with our drawings for our particular project, and we're going to do a bit of group work together. And that's actually very typical of what you would see in a workplace as well. At this point of the project, you would have that design team meeting and sit down around the table together and look at the drawings and analyse them together and come up with a solution together. Not just myself and Lisa telling you what's actually going to happen with the structure, but we will also want your feedback into that, and your anything you've got to contribute, more than welcome.
The good thing about what you've already been through is you're starting to build a bank of knowledge that we can keep adding to now. We're not in the point now where it's starting from scratch. We can start talking about foundations and footings and walls and floors and roofs, and things are starting to pop up automatically in your minds, and we can start adding information to that. One of the best resources for this particular time in the studies is this Building Construction Illustrated. So obviously we have one right here. I think there's a second one floating around somewhere as well. There would have been, this is the one out of your office, and I think there would have been one out of my office as well. Okay. And I have some scanned pages out of it that I can pop up on the screen, and obviously there's lots of copies of this in the library, and I have a feeling you could probably find a PDF version on the internet. So yes, I think you can get this one pretty easily. It's very good. Now, it's not suitable really for residential. There's some information in there that is some parts residential, but it is mostly commercial. So that's why it comes up for AT2 and AT3. It's mostly commercial. It's also really good because it's quite universal. It's not necessarily specifically cyclonic, but it does cover that. Some areas where it might be earthquake-resistant construction or cyclone-resistant construction, there's a special section in there. But these are the kinds of principles that you will come across all the time. They're quite typical construction systems that you'll see frequently, so it's a good textbook for that. I really like, and you can see on the screen, I really like the way they sketch in this particular book. So you'll get different views in elevation, plan, or section, and then you'll get three-dimensional views, which can be really informative. Isometric cutaways. A cutaway is where you can see the layers inside something that's three-dimensional. There's not one on the screen there to reference at the moment, but it's if you see a big sweeping curve and there are several layers of materials all popping out behind, that's called a cutaway, which can be really helpful to be able to describe a system. Because obviously construction doesn't work in isolation. They're systems, they're materials that work together. And so to be able to see the different components is really, really helpful. Is it the online library one, is it, that you can see? Oh. So Adriana's just reminded me.
It's only like a few pages.
Oh. Okay, at a time, yes, I'm with you. Yeah, I did that the other day for a textbook for myself. So through CDU Library Systems, you can look at this book online. It's an e-book that the library has. You can't download the whole thing. You can download, 20 pages at a time, but you can view it online in its entirety anytime, everybody all at once. So you don't have to buy it. This author, Francis D.K. Ching, has a particular gift for this kind of book. So if you search him, you'll actually find he's got quite a few that are worth looking into. Building Construction Illustrated, yeah. So last time we looked at our Class 2 building, we were very specific about what we were looking up. We were specifically looking at the sketches that we have and comparing those with the NCC to see what rules and compliance we would need to implement going forward in the project. So everybody's still got their checklist and the sketches and the handwritten notes, because we will come back to those later on. We're just going to step away for it briefly and have a bit of a look at some construction systems on their own in isolation, and then we'll come back and apply some of that knowledge to the project itself. Does everybody want to try finding the Building Construction Illustrated textbook in the CDU library database? So, I shouldn't say database, in the actual summon search in CDU library. I'll do it on the screen for you at the same time so you can see what to do, and we'll see if it works for everybody at the same time. We have a tendency as a class to ruin things on the internet sometimes by all doing things together. The collective input sometimes tests systems, doesn't it? On the main web page, if you click on the library link at the very top, the library search here is called a summon search, like you want to summon something up. It's a lot more intuitive than library searches used to be. To search in a library database in the past, you had to follow formal Boolean searching terms. These days, searches in library databases are a little bit more intuitive, a bit more like you would find in perhaps Google or something like that. So if I just simply type in Building Construction Illustrated, it should come up. There we go. 3 versions, lovely. So 2014, 2008 and 1943. I think we'll just leave 1943 back there. That would be really cute to look at though if you had nothing but time. This is the one that we want. It's the same front, and I'll just click on Online Access. It's got the same title. And you'll see here it just says Read Online. So you can do that anywhere, anytime, at home, on the internet. Typically when you log in, it will ask for your authentication through the library portal, not necessarily the CDU portal that you're used to, but just as you do this process, a pop-up might come up. If you have access issues with that, try a different browser, because Chrome is often better than Safari or Firefox for this particular portal. So we've got our Building Construction Illustrated, Francis D.K. Ching. On the left-hand side, it's got all the different chapters, just like we like. Couldn't ask for better. So I'm just going to go very briefly, quickly read through the headings. If I can get the screen to stay still. The headings of foundation types. Oh my, just stop now. Yeah, it's got a mind of its own, doesn't it? So foundation systems, and sometimes in construction you might have to construct the foundation a little. So I mentioned the other day, if you're excavating significantly, you might need to support the sides of that excavated space to make sure there isn't a collapse, because there might be significant buildings adjacent. So there's a real art to doing good foundation work at a construction level, at a commercial level. So types of foundation systems, underpinning, which is a bit like what I was talking about. We use this word underpinning quite a lot. It simply just means the stuff that's underneath that everything else is built upon. So you have underpinning knowledge that you're learning at the moment that your career will be built upon. This is underpinning in a more literal sense. excavation support systems, there we go. Shallow foundations, spread footings, foundation walls, column footings, foundations on sloping ground, concrete slabs on grade, pole foundations, deep foundations, pile foundations. I think that last one there is called Cassian. Is that pronounced correctly, do you think? Cassian foundations. I couldn't tell you what they are without checking myself. And then it goes on to floor systems. I think we might just go with types of foundation systems and try not to get too carried away, because we could spend months
going through all the different
reading all of this. So I just want to show you where the information is. A bit like not having to memorise the NCC. Don't expect you to memorise every possible construction system. Commercial construction is a vast range of construction. So we're going to look specifically in context at our Class 2 project, and we're going to look specifically in context at our Class 3 project. And we've chosen projects that replicate construction systems we expect you will experience regularly working here in Darwin. But I want you to be aware that there's more out there than just those versions. Excuse me. So we've got a little indication here on this diagram, and I apologise the screen's not terrifically large, but they've just showed this section that they would consider shallow foundations, and then the section that they would consider deep foundations. And I'm going to do a quick Google search in the morning tea break or at lunchtime for a picture I have seen on the internet of these kinds of buildings. See how we've got these pad footings that spread the immediate load, and then these piles that are driven into the earth. I've actually seen where along a riverbank, buildings that size have tipped over, and all these piles have popped up out of the ground. So there was a big flood, and a lot of buildings, apartment buildings across the river, like down the riverbank, all just collapsed, fell over, and everything just popped out of the ground. Extraordinary scene, extraordinary. But an excellent indication of what it looks like in real life that you couldn't normally see because it's under the ground.
Where was it?
China, I think. Yeah. Yeah, awful. Underpinning. So that's an excellent section diagram of how you might create underpinning. Today, we might observe something a little bit like this in our investigations of Class 2 buildings, because it's often quite heavy concrete construction, and you have to make sure that you've got plenty of support underneath to make sure that the building doesn't do what I just described. A little description here. It says underpinning refers to the process of rebuilding or strengthening. I need a little bit more clarity in my writing there. Bear with me. Underpinning refers to the process of rebuilding or strengthening the foundation of an existing building or extending it when a new excavation in adjoining property is deeper than the existing foundation, providing temporary support while an existing foundation is repaired, strengthened or deepened. Needle beams are passed through the foundation wall and carried by hydraulic jacks at the shores. So these are the shore, where it's shoring up that earth to make sure that it doesn't collapse. So we've got these shoring up here where the trenches are excavated and pushing it back.
If you want to see a good example of this, you know the Chinatown car park in the city?
Oh yeah?
On Smith Street. Go into the Chinatown car park and go up to maybe level 2 or 3. And drive in there without paying. You only pay if you actually park. And have a look at the huge deep excavation that was to be a Chinatown building at the back of that. So this site is basically, you know, where the cinema is on Mitchell Street.
Oh.
If you walk between the cinema and down towards the corner where Shenanigans is there, the whole fence along that there is where it's a shutter. You can't see above it. You can't see into it. Behind that fence is the most deepest excavation. I'm not sure how many stories down it's gone, but it's quite deep. And the funding for the building stopped. But the excavation has been left there, and they've actually gone in and poured concrete on all the sides of the excavation to stop it falling inwards. we've actually built walls around it, which is a type of shoring. But yeah, if you happen to be in the city and you've got a few minutes one day, just take a drive in around the car park and
you can look
stop
down
for a moment. You can look right down
wow.
at the excavation.
There you go. So we've got some shoring up here, examples, and then some props as well that can often be used. And you might see those as well in place when new precast walls are installed and get held in place temporarily while you do the rest of the construction. So shallow foundations, we talked a bit the other day, I can't say yesterday because we had yesterday, but the other day about pad footings and the way that can be used to hold the load of a significant construction system above it and prevent it from settling too far into the earth. So just these are good demonstrations of how loads are distributed and the forces. And then these dots here are reinforcing. It's just a shape. So quite shallow foundations. And then you can see them in action underneath walls and columns. Terrific diagrams.
This will be like engineering job, right?
Oh yes. Oh yes. Yeah. All engineers' jobs. All of it. Yeah. Yeah.
But you do
Hence,
need to
us
be
not.
sitting in a design team meeting every now and again, and the engineers will be talking with all of this terminology.
Yeah.
And you do need to have an understanding of what it is they're referring to when they say, we're going to require pile foundations. There's no point in sitting there going, that's your job, I've no idea
Yeah.
what you're talking about.
Yeah.
You just need to have the vocabulary. You need to have gone through this book and just have an understanding of what that looks like. But you won't be sizing the foundation. You won't be the person deciding which foundation system needs to be used. That's an engineer's job. Structural engineers do that work.
Yeah. Yeah.
Reassuring.
Yeah.
Yeah.
It's a lot.
Yeah.
Yeah.
Yeah. But it's sufficient to say, like, and also what we will be doing now later on today is we'll be looking at our AT2 and we will be determining what the structural system is. Now we already have that set of drawings, so it's fairly clear what the structural system is. But what we want you guys to do is identify the system, be able to put the vocabulary on that system and explain, if you have to explain that to somebody else, for instance, if you're the person, you're leading the project and the structural engineer tells you what the system is, then you need to be able to explain that system perhaps to your, hydraulics engineer at a separate meeting. So you're going to need to have the words, you're going to need to have an understanding of what the system is.
This one's a page about foundation walls, so a little bit more about that shoring. And I just wanted to show you, so this is where you can see the forces of the earth that have been cut away and excavated are being held back by the wall. And then just at the bottom here you can see a bit of that drainage that I was referring to the other day. So we're talking about how you don't want moisture building up behind walls that you build. And so this is a pipe that has slots cut into it so the water can get into it. And then a looser gravelled earth, because if you compact the soil too hard around that drainage, the water can never get to it. So there's loose gravel, and I won't say loose, it's tightly compacted, but it's larger pebbles which have natural gaps within them so that the water can seep through and then get into the drainage and be channeled away. Really fantastic diagrams. And this is a slightly smaller scale, which is probably a bit more like what we're comfortable with. Foundation walls, framing, blockwork. And we will cover a little bit of blockwork today. We're a little bit ahead of where we need to be, or let me just say the Class 1 and 10 class are a little bit behind where they need to be because we didn't get a chance to cover the way the courses work in blockwork construction the other day. So we'll touch on that today and then we'll get a bit of a repetition when we come back to it for the Class 1 and 10 project. What have we got then? And foundation walls a bit more. Lots of different ways that you can do that. Here we go. And then it moves into footings. Have we gone too far? Foundation walls. Column footings, 3.1. Oh no, it's just different footings. That's okay. So our column footings, and this is not a bad diagram with the reinforcing within the column. So remember I talked the other day about the ligatures that would go around strips of reinforcing within a pier footing. This is a good indication of the overlap of reinforcing and the ligatures that hold them together, so you can get a bit of an idea of how that works. And then in plan view as well directly. So this is true if we've got a section view or a detail view, if you like, of the way the footing would work, how it looks in plan view, and then how it looks in 3 dimensions as well. So terrific illustrations. And they're the kinds of things that you might like to trace over to then be able to annotate in your report. Remember how you traced over the chain of strength diagram on the screen? You could use this to help you create images in your report that can describe the system that you're trying to specify for the report.
But you can copy and paste it out using your Bluebeam PDF editor.
That's true, that's true. It's hard to get rid of the text, although does Bluebeam let you pull out there? Well, if you get fancy. So this one's a little different. It's got a saddle that holds the column, often quite good for timber columns in other places that don't have termites. But even here, you can, if you can get the termite up off the, get the wood up off the ground a little bit with the saddle, then you're at less risk of infestation. So you have a footing under the ground and then there's steel embedded in it and there's bolts through this piece of timber, and you can actually place a gap. This one doesn't have it, but you can actually put a gap between the bottom of the timber and the ground and create a space so the termites can't reach it. They're quite determined, these termites, so you don't see that very often. I have seen it occasionally, but you don't see it very often. It can be better if you've got a timber feature. So for example, if you've got even in a really lovely residential or in a particularly nice commercial. So I'm thinking about the airport hotel, you know, the lovely resort with a big entrance by the airport. If you've got, say, a plinth of some sort that's got, oh, that's a bit wide, but you've got a concrete base that could be quite tall, and then you might have that saddle holding the timber here, so that could be quite high. Or you could have a steel column and clad the outside with timber. That's quite common as well, where it's simply just a skin of timber around the outside. But if you get it up a little bit higher, it's safer for the termites and can look really, really good.
And even in areas where you don't have huge termite issues like we do, it's really good to get timber off the ground just for so it's not getting wet
deterioration
at the bottom and rotting with wet rot.
There are borers. There are other insects other than termites that can damage timber. Interstate.
So, yeah, when I go interstate, especially down in Adelaide, I see this type of detail a lot. It's quite a nice detail board. They've just used lots of timber posts, but they've just lifted them off the ground.
This other column shows the way that our portal frame footing will work. So we'll come back to that later. But it's pad footing underneath, or it might be this long pier like we talked about the other day. And then you've got the reinforcing coming up and popping up through the bottom of a plate that's just bedded on a slight plinth, again for water shedding. Remember we talked about having that shedding of water if there's rain or hosing or any water inundation. You don't want it sitting here and corroding the structure. So there's a little plinth and then the steel plate, and the reinforcing pops up and it's threaded, and there are bolts here, and then the actual structure is welded to the plate. So the structure, this I-beam, you can see it's in the shape of an I, a universal column. I shouldn't say an I-beam. The I is the shape and it's in the vertical, so it's a column, not a beam, but a universal column that then just sits on top of that. And the single pieces of reinforcing steel go below it into the ground.
So just on that one, the chain of strength, like we spoke about the other day, is that you have the pad footing and you've got that little concrete plinth, but then you've got the plate, which is connected to the pad footing by the reinforcing and the bolt down of that, and then the column is welded to the plate. So the chain of strength is footing, plate, column.
Good diagram there of sloping ground. And some of the angles that you will probably need to maintain to help subsidence, prevent subsidence. So you don't want the soil that you have coming down unexpectedly. So if you've got an adequate slope, then the soil is more likely to stay in place.
So they're talking about the degrees, 45 degrees there. So your batter, it's often referred to as batter. should be, there's a distance here, the maximum distance that you want the batter to begin away from the building. Your line of building, the line of your
12 metres, I think it says there, yeah.
What does that say?
Yeah, 12 metres.
So 12 metres. I've seen that reduced.
Yeah, that's kind of the maximum, yeah.
Again, that's an engineer's job to tell you what this dimension can be. And then this is the start point of your batter. This is referred to as the batter, the slope down here. And then the slope of the batter should be the full maximum of 45 degrees. In fact, I would want that probably around 30 degrees. So. Yeah. And that's to stop, if this earth that's here starts to fall away down a hillside, this is all compromised. The footings of this building is compromised. And that's why we have these minimum dimensions and stuff for creating that batter. You'll often have to look at batters where you've brought in a lot of fill to a site. So obviously, when we bring in a lot of fill to a site, we don't bring in fill for the entire site. We build it in to build a pad for the footings to be built into. So that pad, that is earth, that is soil pad, I'm talking about now, not concrete pad, can be built up. And then that has to be greater than where the footings are, because you want to allow a dimension here that's further out from the footings, and then it slopes down off that. So your house is quite often built up on a bit of a pad. And then, of course, you can consider how you're going to landscape out here after that. But these are sort of minimum dimensions for structural purposes, not just for landscaping.
Thank you. Concrete slabs on grade.
Let's talk about layering, is it?
Yeah.
That similar information is also in NCC.
A little, very specific, but just on the class 1 and 10 side of things. For the class 2 and 3 to 9, an engineer would have to determine that.
So I think that's referring to the different layers and build-ups that you might need to build up that pad that I'm telling you about. So it's very specific how the layers need to go in. Actually, the structure down below.
So it just says a concrete slab may be placed at or near grade level to serve as a combined floor and foundation system. And the suitability of a concrete slab for such use depends on the geographic location, topography, soil characteristics of the site, and the design of the superstructure. So that's the next level up, the structure that's over the top. Concrete slabs on grade require the support of a level, stable, uniformly dense or properly compacted soil base containing no organic matter. So we've talked a little bit about compaction and soil and fill and voids that are created by decomposing organic matter. When placed over soil of low bearing capacity or over highly compressible or expansive soils, so there are movable sites that we were talking about, a concrete ground slab must be designed as a mat or raft foundation. So there's our raft, our waffle slab, the one with the multiple lines, so everything moves together, as a raft foundation, which requires professional analysis and design by a qualified structural engineer. And there's a couple of diagrams there. So that's using construction to create the foundation and then building the superstructure over the top of it.
And this diagram is showing you about the layers of how you would build up to make that solid pad for the footings to sit into.
Yeah.
And look, I won't go through all the different layers.
No, they've got concrete additives and base coarse gravel and different layers.
Generally, there's a note that the structural engineer will give you, and it will talk about bringing in your fill and compacting it. I think it's the 250 millimeters high, so you only get in 250 millimeters high of fill. You must compact it, so get the roller out and compact that down, and then you come and you build another layer, and that's how we get a very solid base for our footings. And so when we draw. Yesterday we looked at the hatch we might draw for earth. To draw that actually correctly, you should be drawing it in bands of 250 millimeters and talking about having that compacted at each of those. But that's all about building a base, and again, it really is in the realm of the structural engineer.
Or the civil.
Or civil.
Civil side of things. Yeah.
So, when we're talking about, is it like like a big hole in the ground, and then the bottom of the hole will be padded to make it to like a certain,
Yeah.
Correct.
and then footing the
Yep.
field.
Yep. Unless by some miracle the soil is exactly the compaction that you want,
But it could
which
be
is pretty rare.
rock or something.
Yeah.
If
Yep.
you've got
Yep.
rock, you won't be doing that. You'll
No.
be building on the rock.
Yeah.
Yeah.
Yep. Start again. Yep. So you might have to blast to get down a fair way, and then you'll add to build it back up. Yeah.
But what we want to avoid all the time is to have any organic material in that fill. So the quality of the fill needs to be really high. It needs to be, already be a gravel, clean gravel, cleaned, washed out gravel. The issue with the organic material is that if you do have it, can I go back up to that diagram where we've got all the layers? If you've got a rotting tree in this layer here somewhere, a big chunk of a tree, eventually that's just going to leave a hole here, and what's going to happen is that all of this starts to compact down to fill that void. And if you've got your footing sitting here on the top of that, that's going to start falling down. If we've got a building that's like this, and we've got one pad here, and this pad is getting compromised by a void in the fill, then the whole building starts to twist and turn, and the level of that's cracking. That's really structural defects in your building. So the quality of fill coming onto a building site to create a good solid pad for the foundation, a good solid foundation for the footing, is essential. But again, in the realm of structural engineering.
There's just a little bit here about, in those concrete slabs on grade, isolation joints and construction joints. So we've mentioned those already, where you create a space for expansion and contraction to occur so that it's not extrapolated out over the entire slab and then damaged on its own. So it will do the cracking and create that construction joint on its own if you don't manage it yourself. And they're quite good. They're just a bit of information about isolation joints or expansion joints and construction joints. And I talked yesterday, remember I drew that diagram with the board with the little indent where you cut it? So these are the same explanations here repeated again. So you've got some coverage that you can go over again. Control joints create lines of weakness so that the cracking that may result from tensile stresses, so pulling and pushing, tensile stresses occurring along predetermined lines, and then space control joints in exposed concrete, so every sort of between 4.5 and 6 metres, or wherever required to break an irregular shape in the slab into a square or rectangular sections. I meant to mention the other day too, we talked a bit about having two different types of slabs abutting one another. This is the texture, this is the foam, compression foam that you put between the two slabs. It's not always this shallow, you can get them quite deep as well depending on the size of the slab thickness that you want to put it between. But it's adhesive on one side, so you take the adhesion off and you've got a finished slab, and you place this against the slab that you've already got before you pour the next one. And it's actually got a little separate section right at the top here, so this goes to the slab you want to, right up to the height, but the next slab might be 10 mil down, and then you can just peel that off at the end, and you're left with a foam surface between the two slabs. And this allows that expansion and contraction at the outer edge, because if you encase one slab inside another and don't allow for expansion and contraction, you'll get deformation. It's kind of nifty. Oh, look, and we've got a sketch happening as we speak. Yep. So that top little piece gets all messy with splashes of concrete, you can just tear it off.
And then in here,
Material much larger.
Yeah. Oh, look. Yeah. Oh, that's indestructible, yep. This kind of, here we go, extruded polystyrene foam insulation. Fancy name for it. Hmm. I've just skimmed right past a few construction details that will be moderately familiar to you already because we've discussed them the other day. Edges with connections to walls and hold down rods and reinforcing in them. So I'll let you read them in your own time rather than repeating them. But what I would like to just highlight is this pole foundations detail. It's a terrific drawing. It has some relevance to the way we construct here, and it's a little bit of an overlap with the Class 1 and 10 construction. But pole foundations are particularly popular by a couple of different designers around Australia, and there are a couple of buildings. There's one residence in Palmerston that's a traditional pole home where the actual timber poles, they're quite significant. So we're not talking column and beam construction. It's a special timber pole construction rather than the structural side of things. But definitely worth a look if you want to have a bit of a read. It looks like they're referencing the loads and the way it works. And you can see the cross bracing they've specified as well for the same reason that we do, that it would be subject to wind forces and raking.
So I think the difference here is that the pole that you see coming from this level
It's all the same.
is actually the same pole is going right down in to be the actual the footing for the building, and so in this diagram the footing actually continues to this level here. Whereas where we have an elevated house, we have a footing that sits just below the ground, and then we have a post that connects at ground level. But that post isn't part of the footing.
No.
But in this case, this whole pole is actually the footing.
Yeah. And they get treated and protected and things like that. It's quite nifty.
Generally, we think footing is in ground, but that particular footing tends to extend from the ground right up until it reaches there.
And they've got some
horizontal structural member.
They've got some cool information about how to connect to it, and you can notch into those timber trunks because they're quite substantial. Pole construction, yes, is big timber trunks, very straight, wide timber. Yep, special. Yes, pile is different, you're right.
Pile is concrete.
Yep. All right, so deep foundations. Deep foundations extend down through unsuitable or unstable soil to transfer building loads to a more appropriate bearing stratum of rock or dense sands and gravels well below the superstructure, so super being above. The two principal types of deep foundations are pile footings, pile foundations, and caisson foundations. A pile foundation is a system of end-bearing or friction piles, pile caps and tie beams for transferring building loads down to a suitable bearing stratum. So there's just a pretty good indication here. And I apologise for leaching into load-bearing talk already. That's quite advanced, and we'll head into that in the 4005 unit. But you're choosing foundation and footing systems to account for the pressure that's going to come from the building itself and the people and the occupants and the activities that happen in it. So there's a little bit of a relationship there. And that's really all we're dealing with at this point. So you can see they've got what they call a column load. So if this was the column in our car park, for example, bearing the weight of the transfer slab and then the apartments above, the weight would be coming down. And they've got a shallow footing to begin with, and then the deep pile footings underneath that, which is what we saw on the first page. They've got similar here as, I won't call this an edge, but it's just a beam foundation, a beam footing, and then wider parts where the main loads come down, and then the caissons underneath, or the piles.
Well, your structure has loads. So if this is the column in, for instance, a car park, with all the car parks with multiple columns all around the place, that column has to go down onto either a pad or it could be a whole slab. But then that particular part of the foundation there, the footing, needs to transfer that load back down into, it could be a pad footing that's doing the load on its own because the ground is really stable underneath it, or if the ground isn't so stable, the pad itself needs to be stabilised. by adding these piles below it, and they go further down into the ground until they reach stable conditions down there. But they are the actual piles, not this part.
Yeah, the pad footing and then the piles, yep.
The pad footing, column, pad footing, and piles. Again, it's that chain of where the loads are being transferred down into the ground. So you'd often use these piles in wetlands, which we have lots of around Darwin. But you know, if you are, we tend not to construct on the wetland. But for instance, if you were ever designing, you know, a tourist visitor centre that overlooked the wetlands, you certainly wouldn't be trying to, you know, build your standard foundations on top of what is a floodplain. You'd be trying to get really down below that until you get right down to stable soil. So certainly that's an area of very sandy soil. We see pile footing being used.
And if you think about bridges that take you across water, they don't just float, obviously. They have to go down and down and down and down and down into the seabed until they hit something that's not all muddy and sloppy.
Yeah.
Some different materials that you can use to construct those piles: timber, steel beams, or concrete.
A lot of times piles are done in concrete, and they have like it's a huge drill that comes on site, and it's turning, and as it's turning, it's lifting the earth out, so it's creating a shaft, I suppose, in the earth, and a void. And so one side of the drill is bringing the earth out, and the other side is pouring concrete as that happens, so it doesn't collapse. It's really
that's impressive.
Quite an impressive piece of equipment, but expensive to drill pile foundations because of that piece of equipment.
So different diagrams of how they might be constructed and what they might look like. And they mentioned this last one here, micro piles. Probably the closest thing that I can find in this textbook that is somewhat like the pier footing that we might reference for our elevated house, because an alternative to having the cast-in post, the cast-in column, is to have reinforcing that goes in, like I talked about. And that's often how it's drawn, with the steel plate at the top. So this would be the steel plate at ground level, and this would be the reinforcing going into the drilled hole, and then you would fill it with concrete, and it would hold that reinforcing in there. So it's probably the micropole is probably the closest thing to what we would say we do up here typically. And the Cassian foundations. So a little bit of a splay at the bottom for those ones, a little bit different. It says Cassians are cast in place, plain or reinforced concrete piers formed by boring with a large auger. So that was what I mentioned the other day, those augers that we've got on a much smaller basis for residential. By boring with a large auger or excavating by hand a shaft in the earth to a suitable bearing stratum and filling the shaft with concrete. For this reason, they are also referred to as drilled piles or piers.
So they really are still piles, but they're just that method.
Just a special pile, yep.
The auger that will
correct.
Drill and pour concrete at the same time,
yep.
simultaneously. And
it just says the base of a Cassian may be enlarged into a bell shape to increase its bearing area and resist uplift from soil expansion. The bell may be excavated by hand or be formed by a bucket attachment to an earth auger that has a set of retractable blades. All sounds very technical and very cool. No. And you can see they're trying to illustrate that it's coming down to a suitable bearing of sand or rock. That's really the intention of good foundations, is to either get to or use solid, firm, compacted, non-movable ground. That's all we're really trying to achieve. Just sometimes the topography and the site and the location makes that a little harder. Does anybody have any questions about foundations?
Sorry, so the hole
yeah.
for that
Cassian, yep.
So it's stuck or like drilled?
Yes, it's drilled, like Sandra said, with a big auger.
The earth is coming out one side of the drill, and the concrete is actually being poured at the side.
Yeah, you know, the spiral. Yeah.
They go right down.
And then do they put like around it? Like
No, the concrete was set in. It's
in
almost
the hole.
like they're using the earth as the cast for the concrete. It's all done in one motion, so that it doesn't collapse in, or that you actually have the earth there. But it's very specialised.
It is, yep.
Of engineering,
Yep. And if you're ever involved, get on site and have a big look and get excited and be, really love it. Excellent.
The engineers will love you if you're all
Yes.
excited about that.
Now, would you guys mind terribly, I just stopped for 5 minutes and grabbed a cuppa?